All right, so here we're gonna go into some of the properties here of the eigenvalues, the eigenvectors. These are helpful because it simplifies or excuse me. It can reduce some of our calculations here. All right, so here, recall here when we talked about an eigenvalue, we stated that an eigenvalue was for any non-zero vector. Lambda was an eigenvalue when it had this particular property, right? In other words, it changed matrix multiplication into a scalar operation, right? Which in itself simplifies some computations here. Okay, now our first theorem that we're gonna go over here is this theorem EDELI. So this has to do with linear independence. Right, so here, all right, so theorem EDELI. All right, so what this theorem states, all right, is that if I have a set of vectors, eigenvectors, right, so here if x1, x2, all the way up to xp are eigenvectors of A with distinct eigenvalues. Okay, so if that's the case, right, then the set, so those are my hypotheses, then the set x1 through xp is linearly independent. All right, now that is quite the property since these are dealing with completely different null spaces of a matrix, right? But the set of them, as long as they come from distinct eigenvalues, right, it forms a linearly independent set, right? Even though they come from different they're not sizes, but different spaces. Okay, so that is one of the first kind of properties here. All right, so what this is kind of telling me, and we'll see that later when we talk about similar matrices, right, and something called not a similarity, but diagonalization, right? We'll see how that plays a part into those types of operations, right? And a matrix with n distinct eigenvalues automatically has n linearly independent eigenvectors, right? Because we know those eigenvectors are non-zero. So if there's n eigenvalues for an n by n matrix, then we have n linearly independent eigenvectors. Okay, so now a couple of other more computational properties here that are useful here. So the first one is we have theorem ESMM. So this has to do with scalar multiples, right? So for this one, what this tells me is that, right, if excuse me here. Okay, if lambda is an eigenvalue of A with eigenvector x, then, right, alpha lambda is an eigenvalue of alpha A. Okay, so now we could see this, right? If we have alpha A times x, right, a non-zero vector, that's the same as I can associate these differently, alpha x, right? But I know lambda is an eigenvalue of a, so that means that this can be rewritten as lambda x. And then also, hence, we can write this as associated differently. So now we see that alpha lambda is an eigenvalue of lambda. Let me say that one more time. Alpha lambda is an eigenvalue of alpha a. Okay. All right. So that's a nice consequence here. Another one is that for powers of matrices, so this is theorem EOMP. Okay, so this states that if, again, lambda is an eigenvalue, of A. Okay, so that is true, then lambda s is an eigenvalue of AS. All right, for any non-negative integer. All right, so that's great. So now we can determine, if we know the eigenvalues for A, we know the eigenvalues for any powers of A, right? It simplifies to just taking the powers of the eigenvalues, right? Which is a nice consequence here. Okay, so now let's take a look at our next theorem here. Now this one, I'm gonna show the, I'm gonna bring the textbook into play because this one is, it's a bit involved. There's just a lot going on here. So theorem EP. M. Okay, so what this states here, so let me bring this up here. All right, so here. Okay, so we're looking at theorem EPM, so eigenvalues of the polynomial matrix, which is something we haven't talked about here. So here we'll look at how it's defined and then how it'll come into play for our, how to use it in practice here. Okay, so the theorem states, suppose A is a square matrix and lambda is an eigenvalue of A. Now let Q of x be a polynomial in the variable x, then Q lambda, so the polynomial itself, is an eigenvalue of the matrix QA. Okay, so here, let's take a look at, first of all, how we define QA, right? So x being a non-zero vector, and we define it here as, again, same coefficients. So now we can treat a polynomial of a matrix is, instead of having the variable x, we have the matrix A. So a to the 0, a to the first power, a2, etc., a to the m. And then we have this vector x. Right, and again, just you can distribute x, then matrix multiplication, right? We distribute here on the right, and we get the corresponding equation here, right? And from there, just simplifying, right? Associating it in a different manner here, and then applying what we know about A having eigenvalue lambda, and then we can plug that in, right? And now we can again factor out an x, and we get a naught lambda 0 plus a1 lambda 1, etc. Right? So now we get a polynomial in lambda, right? Q of lambda. Okay, and again, x is non-zero since it is an eigenvector. Okay? All right, so it is an eigenvector of A. Excuse me. Okay, so that is another property here of our eigenvalues here. And now our next property has to do with non-singular matrices. Okay, so for this one we have, if A is non-singular, so this is theorem EIMP. m. All right, so theorem EIM states that if A is non-singular, and lambda is an eigenvalue of A, okay, an eigenvalue on A, then 1 over lambda is an eigenvalue of A inverse. Okay, all right. And again, here we'll see in the next video why we don't have to worry about lambda being 0, all right? Because we're assuming here that A is non-singular, so lambda being 0 is not possible. Again, we'll put that more into a theorem. We'll put that into a theorem in the next video, but for now, we can assume this. As long, again, A is non-singular, lambda is an eigenvalue of A, then for the inverse, you just take essentially the inverse of a scalar, which is 1 over the scalar, in this case, lambda. All right, so a nice little property here, right? So now this can help us to calculate, for example, let's say that given eigenvalues, right, lambda equals 2, -1 for a matrix A. All right, find the eigenvalues for (3a), a to the 4th, A inverse, and A squared minus 3i. All right, so now the first one, 3a. All right, so for this one, we just have a scalar multiple. All right, so for 3a, the eigenvalues are, we just take those. So 6 and -1 times 3, we get -3. All right. Okay. All right, so that is for 3a, for a to the 4th. Again, using the theorems above, well, I know the 2 eigenvalues, so for a to the 4th, it's simply 2 to the 4th, which is 16, -1 to the 4th, which is 1. Okay. All right, again, right, pretty straightforward here. All right, just applying those theorems, simplify our calculations, don't even need to do any calculations. All right, now for A inverse, right, again here, we're making the assumption, which is true, and in the next video we'll explain why, that this exists, right, and for that, the lambda would be the reciprocal, the inverse of the scalar, so 1/2, or lambda -1, in this case here. Okay, all right. Okay, so for the last one here, that one is where we bring in the matrix polynomial, right? This a squared minus this 3i, right? So the polynomials for this matrix polynomial are going to be p of lambda, right? So I don't need to do any other calculations except other than plugging in lambda here. So we get so our polynomial in lambda is going to be lambda squared minus 3. Okay. All right. That means that p of 2 will be, 4 minus 3, which is equal to 1. And then p of -1, which is 1 minus 3, which is equal to negative 2. All right. Okay. And notice here, very straightforward calculations, basic calculations. So that is how I calculate the eigenvalues of these above matrices without doing intense calculations, right? Again, just on the theorems, applying the theorems that I introduced here in this video.